Good morning, students. This is MD Jarid Ahmed, lecturer in chemistry, Dr. BRR Government College, Jadcherla. Today we are going to discuss the topic phenols. Phenols are the organic compounds, and we will discuss in detail about the phenols, nomenclature of phenols, preparation of phenols, physical and chemical properties of phenols. Aromatic compounds containing one or more OH groups directly attached with carbon of benzene ring are called phenols. Those aromatic compounds which contain one or more hydroxyl groups directly attached with carbon of benzene ring are called phenols. Simplest phenol is carbolic acid, C6H5OH. The term phenol is derived from an old name of benzene, phene. When we remove one hydrogen atom from a phenol, we get phenyl, that is C6H5. Nomenclature of phenols. In IUPAC system, bond OH group is represented as hydroxyl. It is used as a prefix, while benzene part of the molecule is used as suffix. Let us take a few examples for phenols. Phenols are also classified into dihydric phenols, polyhydric phenols, etc. Phenol C6H5OH. Dihydric phenols are further classified into orthohydroxyphenol, metahydroxyphenol, parahydroxyphenol. Orthohydroxyphenol, IUPAC name of orthohydroxyphenol is 1,2 dihydroxybenzene. Common name is catechol. Metahydroxyphenol. In metahydroxyphenol, OH group is attached with meta position. Its IUPAC name is 1,3 dihydroxybenzene. Its common name is resorcinol. Parahydroxyphenol. IUPAC name of parahydroxyphenol is 1,4 dihydroxybenzene. Its common name is hydrophenol. Some more examples for nomenclature. If NO2 group is found on ortho position of phenol molecule, we call it as orthonitrophenol. Its IUPAC name is 2-nitrophenol. If NO2 group is present on meta position, we call it as metanitrophenol or 3-nitrophenol. If NO2 group is present at para position, we call it as paranitrophenol or 4-nitrophenol. If NO2 groups are found at ortho as well as para positions, we call it as 2, 4, 6 trinitrophenol. Common name of 2,4,6 trinitrophenol is picric acid. Structure of phenols. The alcohol function group consists of oxygen atom bonded to sp2 hybridized aromatic carbon atom and hydrogen atom via sigma bond. Both CO and OH bonds are polar. Conjugation exists between an unshared electron pair of the oxygen and benzene ring. This results in as compared to alcohols. Compared to alcohols, a shorter CO bond. Compared to alcohols, phenols contain a shorter CO bond. Compared to alcohols, more basic OH group is present in phenols. Compared to alcohols, more acidic OH proton is found in phenol. Physical properties of phenols. Phenol is a colorless, crystalline, poisonous solid with phenolic order. Melting point of phenol is 41 degrees centigrade, whereas boiling point of phenol is 182 degrees centigrade. Phenol is sparingly soluble in water, forming pink solution at room temperature. Phenol is completely soluble above 68.5 degrees centigrade. Phenol causes blisters on skin. Phenol is used as disinfectant and in washrooms. Acidity of phenols. Phenols are more acidic than alcohols. Phenols are more acidic than alcohols. How can we say phenols are more acidic than alcohols? Based on Ka and pKa values. Already we know that weak acids will have Ka value. K means dissociation constant. All weak acids will have dissociation constants. Among the weak acids, greater the value of Ka, stronger will be the acid. When pKa is equal to minus logarithm of Ka, therefore, if lower Ka value is there, it is understood it will have more acidic nature. So, lower the pKa, higher will be the acidic character. Lower the pKa, higher will be the acidic character. pKa of phenols is approximately equal to 10, whereas pKa of alcohol will be between 16 to 20. So, based on pKa, we can say that phenols are more acidic than alcohols. It means it is understood phenols can release proton more easily than alcohols. When we compare the acidic nature of phenols with those of carboxylic acids, phenols are less acidic than carboxylic acids. It can be understood with the help of pKa value. pKa value of carboxylic acids is approximately equal to 5. So, lower the pKa, higher will be the acidic nature. That's why phenols are more acidic than alcohols but less acidic than carboxylic acids. Phenols are more acidic than alcohols but less acidic than carboxylic acids. Comparison of acidity of phenols and alcohols. Phenol exists as a resonance hybrid of following structures. Look at the resonating structures of phenol. Structure 1 represents the normal structure of phenol. Oxygen atom of phenol has two unshared pair of electrons. Now, if you look at the structure of first structure and second structures are same. If you look at the third structure, fourth structure and fifth structure, these third, fourth and fifth structures represent the resonance hybrid structures of phenol. So when we observe the resonance hybrid structures of phenol, oxygen atom gets positive charge. When oxygen atom gets positive charge, releasing a proton becomes easy. Therefore, phenol can release a proton more easily than that of alcohol because of the possibility of resonance. Due to resonance, oxygen atom acquires a positive charge and hence attracts electron pair of OH bond leading to the release of H plus. So when phenol molecule releases H plus, it becomes phenoxide ion. So releasing of a proton becomes easier than that of alcohols. Phenols can release proton more easily than those of alcohols. Therefore, phenols are more acidic than alcohols. The resulting phenoxide ion is also more stable than alkoxide ion. Carbon atom of COH group of phenol is sp2 hybridized. This carbon atom is more electrophilic than carbon atom in alcohols, where carbon atom is sp3 hybridized. The carbon atom of phenol is sp2 hybridized, whereas carbon atom of alcohols is sp3 hybridized. In phenols, greater inductive effect facilitated release of proton. Due to the greater inductive effect, phenols can release proton more easily. Thus, phenols are more acidic than alcohols because resonance is impossible in alcohols. Resonance is impossible in alcohols, whereas resonance is possible in phenols. Phenoxide ion is more resonance stabilized than phenol. Phenoxide ion is more resonance stabilized than phenol. But in case of alcohol, alkoxide is not stable because there is no possibility for the delocalization of negative charge. When we observe the structure of phenoxide ion, there is a delocalization of negative charge. Negative charge is distributed in benzene molecule. So phenoxide ion is more stable than phenol. Why? Because in phenol, distribution of charge can be found. Positive and negative charge is found in phenol molecule, whereas negative charge is spread over the phenoxide ion. So charge distribution is less stable than charge distribution. Charge separation is less stable than charge distribution, or charge distribution is more stable than charge separation. Charge distribution is more stable than charge separation, therefore phenoxide ion is more stable than phenol. Here phenoxide ion is also more stable than alkoxide ion, because in alkoxide ion there is no possibility for the delocalization of negative charge, whereas in phenoxide ion there is a possibility of delocalization of negative charge. Comparison of acidity of phenols and carboxylic acids. When we see the resonating structures of carboxylic acids, structure 1 represents a carboxylic acid RC double bond OH. If you look at the resonating structure, RC double bond OH plus O minus. Carboxylic acids ionize as RCOOH gives rise to RCOO minus plus H plus. Carboxylic acid releases a proton more easily. The carboxylate anion exhibits following resonating structures. In carboxylate ion, we can find the two resonating structures of carboxylate ion. RC double bond O minus, RCO minus double bond O. These are the two possible structures of carboxylate ion. In carboxylate ion, negative charge is spread over two oxygen atoms. When negative charge is spread over two oxygen atoms, it gives more stability. Therefore, carboxylate ion is more stable than phenoxide ion. Therefore, carboxylic acids are more acidic than phenols. The resonating structures of RCOOH 1 and 2 are not equivalent and hence less stable. The resonating structures of RCOO minus are equivalent and hence more stable. It means that carboxylate ion is more stable than carboxylic acid molecule. Thus, carboxylic acid have tendency to undergo ionization and form more stable carboxylate ion and proton. Carboxylic acid molecule has a tendency to lose a proton more easily. The resonating structures of phenoxide ion are not equivalent. Look at the resonating structures of phenoxide ion. If you observe the resonating structures of phenoxide ion, the negative charge is distributed in benzene nucleus. So, charge distribution is found in phenoxide ion. The resonating structures of RCOO minus are equivalent. Hence, RCOO minus is relatively more resonance stabilized than phenoxide ion. See, in phenoxide ion, negative charge is distributed in benzene nucleus, whereas in carboxylate ion, the negative charge is spread over the two oxygen atoms. In phenoxide ion, negative charge is spread on only one oxygen atom, whereas in carboxylate ion, negative charge is spread over two oxygen atoms. Thus, Carboxylate ion is more stable than phenoxide ion. Carboxylate ion RCO minus is relatively more resonance stabilized than phenoxide ion. Thus, carboxylic acid is more acidic than phenol. Relative acidity order of some common compounds. Carboxylic acid is more acidic than carbonic acid, which is more acidic than phenol, which is more acidic than water, which is more acidic than alcohol. If you look at the relative acidity order, carboxylic acid is more acidic whereas alcohol is least acidic. Effect of substituents on the acidity of phenols. Already we learned that phenols are more acidic than alcohols but less acidic than carboxylic acids. Electron attracting substituents. Electron attracting substituents or electron withdrawing substituents tend to disperse negative charge of the phenoxide ion, thus stabilize the ion and increase the acidity of phenols. So whenever electron attracting substituents are found, then it causes increase the acidity of phenols. If electron releasing substituents means electron donating substituents tend to intensify the charge, destabilize the ion, diminish the resonance and decrease the acidity. Whenever electron releasing groups are found along with the phenol, these electron releasing groups intensify the charge, they destabilize the ion, they diminish the resonance and therefore they decrease the acidity. So one thing remember, whenever electron withdrawing groups are found with phenol, they increase the acidity of phenols. Whenever electron releasing groups are found with phenol, they decrease the acidity of phenols. Preparation of phenol. Look at the preparation of phenol. Reaction of sodium salt of benzene sulfonic acid with the NaOH. Reaction of sodium salt of benzene sulfonic acid with NaOH. Sodium benzene sulfonate. Sodium benzene sulfonate. On fusion with a strong alkali like NaOH at 300 degrees centigrade give sodium phenoxide, which on treatment with HCl gives phenol. See, sodium benzene sulfonate on fusion with strong alkali like sodium hydroxide. Sodium hydroxide gives sodium benzoate. This sodium benzoate on reaction with HCl gives phenol. Besides phenol, we also get NaCl. Second method is base hydrolysis of chlorobenzene, Dow's method. Second method to prepare phenol. Phenol can also be prepared by Dow's method. In this method, chlorobenzene is hydrolyzed by heating with 10% NaOH at 360 degrees centigrade under high pressure to form sodium phenoxide, which on treating with HCl gives phenol. Look at the equation. Chlorobenzene reacts with 10% sodium hydroxide at about 360 degrees centigrade gives sodium benzoate. This sodium benzoate on treating with the sodium benzoate or sodium phenoxide. This sodium phenoxide on treating with HCl gives phenol. Besides phenol, we also get NaCl as a byproduct. Third method, preparation of phenol, acidic oxidation of cumene. Acidic oxidation of cumene. Acidic oxidation of cumene. It is recently developed commercial method for preparation of phenol. Acidic oxidation of cumene is the recently developed commercial method to prepare phenol. Cumene is oxidized by atmospheric oxygen in the presence of metal catalyst into cumene hydroperoxide. So in this method, cumene is converted to cumene hydroperoxide. It means preparation of phenol is carried out in two steps. First step is preparation of cumene hydroperoxide. Second step is treatment with sulfuric acid. So in the first step, cumene is oxidized by atmospheric oxygen in the presence of a metal catalyst, giving rise to cumene hydroperoxide. This cumene hydroperoxide is converted into phenol through acid catalyzed arrangement. Cumene hydroperoxide on treating with the acid catalyst like H2SO4, giving rise to phenol. Besides phenol, we also get acetone. So this is the recently developed commercial method to prepare phenol. So far we studied three methods. Fourth method is preparation of phenol from aryl diazonium salts. Aryl diazonium salts. Phenol can also be prepared from aryl diazonium salts. Any diazonium salt is prepared by reaction of arylamine with nitrous acid. Normally, in this method, phenol is obtained in two steps. In the first step, benzene diazonium salt is obtained. In the second step, benzene diazonium salt undergoes hydrolysis to give phenol. So, first step is formation of benzene diazonium salt. For this purpose, we can take aniline. C6H5NH2 is aniline. Aniline on treating with the nitrous acid at 0 degree centigrade gives benzene diazonium salt. Aniline is converted to give benzene diazonium salt. On treating NaNO2 with HCl gives HNO2. The reacting species is HNO2. Therefore, we get benzene diazonium salt. In the second step, benzene diazonium salt is hydrolyzed to give phenol. Benzene diazonium salt on treating with the H2O in the presence of H2SO4 at about 100 degrees centigrade gives phenol. So far we studied four methods to prepare phenol. Among the four methods, one is commercially prepared method using cumene. After preparation of phenols, let us discuss the reactivity and reactions of phenols. Phenols are very reactive towards electrophilic aromatic substitution. Like benzene undergoes electrophilic substitution reaction, phenols also undergo electrophilic substitution reactions. OH group is strongly activating ortho-para directing group. See, benzene undergoes electrophilic substitution reactions, phenols also undergo electrophilic substitution reactions. These electrophilic substitution reactions which occur in phenols are more vigorous than those which occur in benzene. It means phenols readily undergo electrophilic substitution reactions than those of benzene because OH group is strongly activating group and OH group is ortho-para directing group. OH group is ortho-para directing group. Therefore, whenever phenol undergoes electrophilic substitution reaction, two products may be formed. One is called ortho product, another is called para product. So, phenol on treating with electrophile gives para product and ortho product. Strong activation means milder reaction conditions than those used for benzene. Strong activation means milder reaction conditions than those used for benzene. Nitration. Nitration occurs in benzene, nitration also occurs in phenol. Sulfonation occurs in benzene, sulfonation also occurs in phenol. Halogenation occurs in benzene, halogenation also occurs in phenol. Alkylation occurs in benzene, alkylation also occurs in phenol. Acylation. Acylation occurs in benzene, it also occurs in phenol. Nitrosation does not occur in benzene whereas it occurs in phenol. So, strong activation means milder reaction conditions than those used for benzene. Under milder reaction conditions, phenols undergo electrophilic substitution reactions. Phenols are so activated that poly substitution can be a problem. Phenols are so activated that poly substitution can be a problem. Next, oxidation of phenols. Phenols are very reactive towards oxidizing agent. The oxidation takes place through several steps, eventually destroying the ring. Sodium salt of phenol. Treatment with sodium metal, carboxylation of phenols, Kolbe-Schmidt reaction. Kolbe reaction or Kolbe-Schmidt reaction. In this, it is nothing but carboxylation of sodium salt of phenol. Carboxylation of sodium salt of phenol. Sodium salt of phenol on treating with CO2 is called Kolbe reaction. It is a carboxylation of phenol. Sodium salicylate, sodium orthohydroxybenzoate is in this reaction. Sodium salicylate or sodium orthohydroxybenzoate is formed. Ortho product is isomerized to a para product. Electrophilic center in this reaction. Acidification of the salt gives orthohydroxy acid. If you look at the equation, sodium salt of phenol reacts with carbon dioxide giving rise to ortho product, and also para product. It means since phenols in phenol OH is orthopara directing, we get ortho product as well as para product. Sodium orthohydroxyl benzoate and sodium para-hydroxyl benzoate. These are the two products which occur on treating sodium salt of phenol with carbon dioxide. This reaction is called Kolbe reaction. Thank you.